Welcome to breakout session number 7, Pathways to Net Zero Materials Production. My name is Nathan Forrest. I'm the technical director for the California Nevada Cement Association. I'll be leading this panel. We've got a group of fantastic presenters. Following me will be Hernan Perez, the technical services director for Cemex West region. Following Hernan Perez, you'll hear from me again. We're short a presenter today. Charlie Ray from CalCEMA is out sick. I'm going to do my best to present Charlie's slides. I'm going to go through them quickly so that if I screw anything up, nobody will have time to dwell on it. After me, Amari Jones from Nucor will be up. Amari is the manager of corporate sustainability for the Nucor Corporation, focusing on providing environmental support and expanding decarbonization initiatives to reduce Nucor's enterprise footprint. After Amari, we'll hear from Melissa Zirps with Magrathea Metals. I'm really looking forward to this one. Melissa is a metallurgical engineer at Magrathea, working to build in-house technical knowledge and applications of magnesium metals. They've got a really fantastic process, and I'm looking forward to hearing more about. And finally, we'll hear from Morse from Mango Materials. She's the CEO and founder of Mango, a startup company pioneering the use of methane to produce biodegradable materials. It's going to be interesting as well. All right, before we get going with the rest of the presenters, I thought I'd give a quick update on where the cement industry in California is. Lots of folks so far today have talked about the cement industry, and I thought I would give you a snapshot of what we're actually working on. Hernan's also a part of the cement industry, as are a few of the other people in the room here. So I work for a nonprofit trade association that represents the companies that make cement. You'll see their logos there on the right. And a couple of things you need to understand about our industry. Number one, Senate Bill 596 passed, which mandated by law a trajectory to carbon neutrality for our industry by 2045. So far as we know, this is the only law in the land that's a material-specific, carbon-neutral focused piece of legislation. The good news is that the California cement industry is committed to carbon neutrality. We've released the second version of our roadmap to carbon neutrality, available on our website. If anybody'd like to have a look at it, tell us your opinion on it, you're welcome to do that. My contact information will be on a slide here in a minute. Happy to hear from you on this. One slide here about what's going on with our roadmap to carbon neutrality. This slide outlines the different ways and steps that we're taking to decarbonize our industry, from the process emissions that result from the limestone calcination reaction that we've already heard about today, the industrial heat that we require to drive that process, and of course, electrification. One important thing for you to realize is when you look at this graphic is that every circle on there represents an area in which the cement industry does not fully control our own destiny. We're going to be needing regulatory assistance, legislative assistance, funding assistance, research, et cetera, to make this a reality. And as you saw from the slide regarding the Senate Bill 596, we are on a timeline here. So these are the things we're working on. I'm just going to touch on two of these levers today. The first one, blended cements, and the next to last one there, waste heat recovery. In the area of blended cements, our industry is looking to move to blended cements. There are 4 different types of blended cements under ASTMC 595. If you're part of a public agency, I would encourage you to consider using these in your work. If you're an architect or an engineer, please allow these in your specifications. And if you're an NGO and you want to advocate for something that can make a real difference, I've kind of listed some of the potential impacts up here. This is something that you can advocate for among other agencies, architects, engineers, owners, et cetera, and make a real impact right now. And the reason why it's so important that we focus on decarbonizing cement is because of the impact that it has in concrete. While cement is only a small fraction of concrete by mass, it's responsible for most of the embodied carbon that happens in this building material. And as we know, we build our infrastructure with concrete, not with cement. But by focusing on what we're doing in the cement, we can effectively decarbonize the concrete industry as well. And so that is what we're trying to do, is transition from a market of today's ordinary blended cements to tomorrow's market of blended Portland cements, like the rest of the nation is also working on as well. And one last note here on the other lever I mentioned, waste heat recovery. There's an assembly bill right now, 2109, from Juan Carrillo, that would legislate the ability for the cement industry to economically, effectively capture heat from the process that we have in place already and use that as an energy efficient way to drive some of the electrical equipment in our process. Okay, so that's a quick look at what we're up to right now. There's my contact information. Feel free to reach out. I can talk about cement and concrete for an awfully long time if that's what anybody would like to do. Our first presenter in the panel today is Hernan Perez. Come on up.
Thank you, Nathan, and thank you, UC Davis, for the opportunity to be here today. Because we are not the Googles or the Amazon of the world, and I'm going to have a brief overview of Cemex. Cemex is a cement, ready-mix, aggregates, and urbanization solution company. It's a worldwide company. We have operations in the 4 continents, and we have near 100 countries that we have a networking of cement or construction materials. Cemex is a $15 billion company with more than 43,000 employees, with 60 cement plants, almost 90 million tons of cement we produce, with 1,200 ready-mix plants, and we have the capacity to produce 50 million cubic meters of concrete. We have more than 250 aggregate plants that can produce 140 million tons of aggregates, and more than 360 terminals between cement and aggregates. In the US, we are located more in the southern of the US and the western of the US. We have 8 cement plants. We have also 50 cement terminals and 50 aggregate quarries, and more than 300 ready-mix plants. And going more to the detail, in California, we have around 60 ready-mix plants with the 1 cement operation that is located at Victorville in Southern California. We have 4 cement terminals. 3 of those are marine terminals, and very important of the marine terminals that we have the opportunity to import different powders or cementitious materials. Could be cement, but also could be slag and fly ash. There are materials that are used in concrete to reduce the CO2 of the mixes. Also, we have 3 aggregate terminals and more than 11 aggregate plants. Future in Action. So Future in Action is our plan to, through sustainability, get the climate action reduction of CO2. Cemex is applying this Future in Action around the world, and our main goals are a reduction of 430 kilograms per ton of cementitious. There is a 47% reduction. That's compared to 1990 baseline. Also a reduction of 41% of CO2 emissions in concrete, and to reach 65% clean electricity consumption. Our final or main goal in 2050 is get a net zero emissions across the company. 2 minutes, okay. To achieve this important information about the CO2, Cemex has the option of producing EPDs in the 3 main products that we produce. In cement, in our Victorville plant, we have the EPDs for the Type 1L cement, the Type 2.5 cement, and Stucco cement. We have 65 ready-mix plants, around 65, but we have produced already 5,000 EPDs, and we have the option of produce on-demand EPDs every time that anybody needs an EPD. And we have 4 aggregate facilities with 43 different products that also we have EPDs. After the EPDs that we know that is cradle to gate, We also have sustainability actions. One is the renewable diesel. Around 95% of our fleet is renewable diesel that have a reduction of 75% of the CO2 plus the other benefit. And finally, our cement plant, that is our local plant. We use alternative fuels in the cement plant. Around 22% of the fuel that we use is alternative fuel. We are certified by the Wildlife Habitat Council. We have 4 wind turbines, and we are working in a solar energy system over the plant. We have 2 low emission locomotives at the plant. We have been EPA Energy Star for many years. We provide and produce Type 1L cement. We are working in Type P cement. And finally, we are working on a pilot project of capture and carbon capture and utilization. So that's what I have. Thank you.
All right. Charlie Ray, as I mentioned, is not with us today. He fell ill, so I'm going to try to run through his slides very quickly here. He wanted to talk about policies and what CalCEMA has been up to. For anybody who didn't know, CalCEMA is the California Construction and Industrial Materials Association. They represent mining interests and also ready-mix concrete producers and hot mix asphalt producers. Some of the things he wanted to talk about is the reductions in carbon footprint that has already come in the concrete and asphalt world, things that the CalCEMA members are working on. CalCEMA is a big proponent of recycling. They were responsible for Assembly Bill 2953 last year, which mandated that local agencies allow the use of recycled materials. It was news to me, but there are apparently some public agencies in California that would insist on only virgin materials in their roadway projects, for example. And even the people who make those materials say, hey, that's not a great plan. Let's use recycled materials. And as a result, a lot of additional flexibility came into the asphalt space and the concrete space as well. Portland limestone cement, one of the blended cements that's part of the cement industry's roadmap to carbon neutrality. I mentioned that already. Excuse me. CalCEMA is very involved in the Cal Green code changes coming July 1st. I hope I'm not the first person to break that news to you. There are code changes coming to the way that California does buildings coming in just a couple of months here. CalCEMA is also very involved in Assembly Bill 2446. I don't see him in the room here, but I know that the CARB staffer leading that is here at the symposium today. As far as the Inflation Reduction Act, one of the main points Charlie wanted to make is that this is really important to both the concrete industry and the asphalt industry as far as driving the concept of low carbon materials into the mainstream, right? The more and more these materials are used and are required to be used, the more common they're going to be, and frankly, the easier they're going to be to produce en masse. And so this is really important here, and noted here that the IRA will leverage funds into construction. And finally, he wanted to make note here that CalCEMA does have a roadmap here to net zero concrete at their website, calcema.org. Net zero concrete will talk all about what the California concrete industry is up to. So hopefully that was quick enough for nobody to notice that those were not my slides, and I didn't really know what was going to go on, but here we are. Next presenter is Amari Jones from Nucor.
All right, good afternoon. All right. Make sure y'all are awake after lunch. So my name's Amari Jones. I'm the Corporate Sustainability Manager for Nucor. In my role, I kind of support all things sustainability for the enterprise. I interface with our R&D teams on just being able to reduce our Scope 1, Scope 2, Scope 3 emissions. We do a lot with policy. Everyone's really talked about IRA and Buy Clean. That affects us a lot as a steel producer. And also we kind of work on a mill level on what we can do to lower our global warming potential. So I'm going to go over just a couple of slides about Nucor and kind of some things that we're working on. So just for a little bit, if those, or who's familiar with Nucor? Oh, great room. All right. Well, then I may go through this quickly. All right, so again, Nucor is the largest steel producer in the United States. We produced about 25.2 million tons of steel and steel products that actually went to outside consumers in 2023. A lot of people, what does that mean, Amari? So we create steel, but we also have over 300 different locations that does the fabrication of steel. So we can do everything from melting your steel to building a building for you that needs to go into any new development that you have. We're actually the largest recycler in North America. So one thing about how we make steel, we use an electric arc furnace, and I'll talk a little bit more about that a little bit later, but we use a lot of recycled content. So we are the largest recycler in North America. We actually do have to get that verified every year. So we actually have 25 EAF steel mills across the United States, and I'll show in the next slide kind of where they're located. We do sell an iconic line, so we talked a lot about what is green steel, how is green steel working. We understood that our customers are looking to meet 2030 and 2050 net zero goals. So because of that, our greenhouse gas footprint is already relatively low, but we also offer a green steel product where we can offset scope 1, 2, and 3 emissions and provide a green steel to our customers. And lastly, we're Fortune 102. So I always like to throw that plug in there for those that aren't familiar with Nucor. We say we're a hidden gem, but we're really proud of the things that we've been doing in the space. So Nucor locations, we're all over the US. So we have about 300 locations across the board. Our 25 steel mills span from Fontana, California, all the way up to Auburn, New York. So we're stationed all kind of around the US as far as our steel mills. So we manufacture plate, we manufacture coil, which is sheet, kind of what goes into automotive, and we manufacture bar, which is rebar, angle iron, kind of things that are used to make this building. So we make all of those materials, and then we also fab them depending on what the end customer is looking for. So I kind of really want to talk about how we make steel. So Nucor has a very low greenhouse gas footprint. We're 60% lower than the global average for steel making, and we're only a third if you compare us to extractive steel making. And a lot of that has to do with how we make steel. We make steel through a circular process. So on average, our recycled content is about 70%. And depending on what type of product, that number can get all the way up to 98%. So we use a lot of scrap to make our material. We use an electric arc furnace, so we do consume large amounts of electricity. But when that product gets end of use, we're able to remelt that product down and create a brand new product. So I always like to show this slide. If everyone made steel the way Nucor made steel, we would eliminate more than 2 billion tons of greenhouse gases per year. Just to put that in comparison, it's equivalent to grounding the entire global airline industry twice. So we're very proud of how we make steel in our low greenhouse gas footprint. But we're not stopping there. We fully understand we do need to continue to decarbonize. We've set 2030 goals as well as 2050 goals on decarbonization just to continue to lower that footprint. We're really big on innovation. We're really big on kind of pushing the needle. How do we become net zero? So kind of 5 big areas that we're looking at. Biocarbon. So can we replace some of our virgin carbon with more biocarbon substitutes? We are making carbon steel, but what are some ways that we can reduce that? Green pig iron is something we use, so it's a raw material that we use, but there are ways for us to make that more sustainably sourced. Carbon sequestration, we did do a partnership with Exxon to transport and store up to 800,000 tons per year of CO2 out of our DRI plant. We've been doing, I know Priya talked about it, we just did a big partnership with Microsoft and Google around just producing more clean energy and more R&D around the clean energy space. And lastly, we've been doing R&D on how we can create near zero emission iron making. I got 10 seconds left, so look forward to answering some questions. Thank y'all.
All right, hi. So I am Melissa Zirps, and I am from Magrathea. So Magrathea is creating new process technology to create electrolytic magnesium metal that is carbon neutral and cost effective to make in the West. Just just a non-disclosure and confidentiality statement. And so Magrathea was founded about 2 years ago by Alex Grant and Jacob Brown, who actually both come from the battery space. And they realized how hard it was going to be able to meet the demand for electric vehicles based on the battery supply chain, and realized we needed more levers. And that's when they started looking into lightweighting and came across magnesium metal. So what is magnesium metal? I know people aren't as familiar with it as they are with aluminum or steel. So magnesium metal can be alloyed and cast into parts for the automotive or aerospace industries. It can also be used in aluminum alloys, and almost every single aluminum alloy has magnesium in it. It can also be used as a reduction agent and is used in making of titanium as well as several other types of metals. So magnesium is a great metal and is impactful, which Alex and Jacob saw, because it is so light. It has the highest strength to weight ratio of any structural metal. Additionally, it's super easy to recycle, and it's incredibly benign to human health, which can't be said about other metals or materials necessarily. So Magrathea is trying to secure a low carbon magnesium for the era of decarbonization. So we are looking to create metal in the West and bring back Western manufacturing, while also decarbonizing the metal industry, which can't be done as easily with a metal like aluminum or steel. While doing this, we are also eliminating the need for mining within the supply chain and saving critical land, such as primary Amazon rainforest. So what is our process? What are we actually doing? Our process is an electrolytic process where we take in brines, seawater, waste brines from sea salt potash production, and we clean them up, get rid of the boron, the sulfur, and then we dry them out to create anhydrous magnesium chloride. We then take that magnesium chloride and, using molten salt electrolysis, separate the magnesium metal and the chlorine to produce magnesium metal, which then gets sent to our foundry and poured into ingots. We have filed 8 provisional patents on this, and 3 of them have already been converted into full patents, or full patent applications. So what is so special about magnesium electrolysis? It's this eutectic here, actually. So this big orange region is for magnesium production, while that little pink area is the Hall-Heroult process for making aluminum. So you can see that that magnesium process, it's really wide and deep, while the Hall-Heroult process is very small. And this means you can change your composition within your electrolyte, as well as the temperature of your cell throughout your process, and still be producing metal, which you cannot do in the Hall-Heroult process. And what's interesting about this is it then becomes incredibly amenable to being able to interweave intermittency into it. So that is solar and wind power, which you could never do in a process like Hall-Heroult. What have we done so far? So we have proven out our technology at the mini pilot scale fully, and we are now commissioning our 2-ton per year pilot plant. And we have made over 10 kilograms of magnesium metal with our molten salt electrolyzer in our Oakland, California facility. So I mentioned before that we are carbon neutral, but we have actually been able to prove this out using a rigorous third-party life cycle assessment that was peer-reviewed by a panel of experts. So as you can see, we have actually proven that our metal is inherently carbon neutral with a footprint of negative 0.1 kilograms of CO2 equivalents per kilogram of metal. And this is a significant improvement compared to any other process to make magnesium today, which is shown there. The way we do this is, of course, using that renewable energy, that wind, solar, but also by creating a byproduct of magnesium oxide. That byproduct is able to sequester carbon and enhance ocean alkalinity, bumping our very small already carbon footprint past 0. Additionally, we believe we can make a cost-effective product, competitive with the magnesium coming out of China using their thermal processes right now. And we believe that this is inherently important to having a viable and impactful product. So we're scaling and building as fast as we can. As I mentioned, we are currently building that pilot plant right now that is 2 tons per year, but we will begin to start building that demonstration plant in the coming months. We're gonna begin on that. That'll be a 200 ton per year facility. And that facility will actually be commercial scale cells, but only 2 of them. From there, we'll have completely scaled up and we'll only need to scale outward to our commercial plant, which will be commissioned in 2028. We have some pretty strong partnerships with the US government. Most notably here would be with the Department of Defense. We have a $28 million public-private partnership with them where they are funding the majority of our scale-up through that demonstration plant. We also have recently announced our supply agreement with a leading natural resource operator, Cargill, who runs a sea salt operation in the San Francisco Bay. They will be providing the waste brines that we'll be using to make metal for both our pilot and our demonstration plant. So if you have any more questions, I'm also happy to answer them. This is our CEO's email address, and he would be happy to hear from you as well. Yeah.
Good afternoon, everyone. I'm Molly Morse, CEO and co-founder of Mango Materials. We've heard about materials, cement, metal, and now we are going to talk about plastics. So my company, Mango Materials, is very passionate about plastics and very concerned about the end of life. What happens to these materials if they end up in our natural ecosystems like our oceans? And the problem, one of the challenges, is that while we should definitely recycle, we're not going to recycle our way out of the problem with plastic pollution. So what do we do about this? Well, our company exists to create biodegradable alternatives to existing plastics. And we actually do this by using biology. So there's bacteria that naturally produce a biopolymer inside their cell walls. It's called PHA, polyhydroxyalkanoate. This is a naturally occurring biopolyester that's actually produced by most living things on planet Earth, including humans. And what happens is this PHA that's produced inside the cell walls can be harvested and formulated into these pellets that are a replacement for everyday plastics. Now, there's many types of biopolymers out there. Some people are familiar with other forms, and one of the unique attributes of PHAs is that they can biodegrade in many environments. Industrial compost, but also backyard compost. Environments where no oxygen's present, like modern landfills and wastewater treatment plants. And even if these materials end up improperly disposed of, they can be naturally consumed by marine microorganisms. So at our company, we formulate those pellets for specific applications, and we make sure that they're always designed for the naturally occurring carbon cycle, which is actually quite tricky. PHA, polyhydroxyalkanoate, it's a naturally occurring biopolyester, as I mentioned. There's many types, it's a whole family. The type of PHA we're very passionate about is called P3HB, poly-3-hydroxybutyrate. This is as technical I'll get on the chemical side today. But through formulation type work, you can adapt that PHA and tailor it for specific formulations. So you can make it into molded goods, fiber extrusion, film, all sorts of different applications. So we work throughout the value chain because this is a different molecule. It melts, it flows, it crystallizes differently. And so if you make this into formulated pellets, there's a whole value chain that has to be worked with that is quite complicated, not just scientifically, but also if you're trying to propose the benefits from an LCA perspective of your material, it's really complicated to educate the whole group. So we work to make pellets for injection molded applications like beach toys. We have a number of customers. Our most advanced one is Natura, a Brazilian cosmetic company. But this can go into a variety of applications in fashion, beauty, 3D printing like ocean products, film, and fiber. Now, PHA is historically made from sugar. You take sugar, you feed it to bacteria, you produce PHA. And we use those sorts of PHAs and we formulate them. But the reason I'm here today is because we also have a unique route to make PHA, and that uses methane as a feedstock. So we use methane actually in the form of biogas from anaerobic digestion. We just recently moved, actually 20 minutes from here, to the Easterly Wastewater Treatment Plant in Vacaville, California. So we use the biogas emissions that would otherwise be flared. We feed that methane in the form of biogas to our bacteria that naturally produce that biopolymer. We transform that into pellets that can be made into an environmentally friendly alternative for existing plastics. And the unique thing is these can anaerobically biodegrade, so they can close the loop theoretically on carbon. Now, why are we using methane? It is a potent greenhouse gas. Some customers could be concerned about sugar and food and the differences in carbon there. But one of the unique things of using methane is we can eventually scale up to produce very low costs of PHA, because methane can be a very cheap form of carbon. It's also the carbon that we have from landfills, from wastewater treatment plants, from agricultural facilities. This is the carbon that we have, and biology has this unique ability to take those various forms of carbon and transform it into what we want, which is things like materials, like plastic substitutes. So our current facility is located in Vacaville, California. This is a recent move. We're looking to scale up there. And we're focused on two things. One, methane fermentation. This is gas fermentation. We need methane and oxygen with our bacteria. And two, the formulation of these materials for end of life, so we can not only decarbonize the source of the material, but also close the loop on carbon. So with that, if you have any questions, you're welcome to contact me. My information is here, and I look forward to the panel. Thank you.
All right, let's have the panel come on up and let's take some questions. Who wants to be first? Don't make me go first.
All right. Hi, Nick Santero with Rivian. Wonderful presentations by everyone, thank you. Amari, question for you. So with steel, Nucor's done an amazing jobs, particularly on recycled content and making mini mills, be part of that process. When we get down to things like DRI, it becomes a little bit trickier to start to decarbonize. I'm wondering if you could talk a little bit about the way we talk about iron ore. How do we get to something approaching zero with just the iron?
Hello? All right. So we actually do have 2 DRI facilities. DRI basically is a raw material that goes into our sheet process to manufacture the quality of steel need for mostly automotive as well as some of our sheet mills. We have one in Trinidad and we have one in Louisiana. So one thing that we've been doing in our Louisiana plant is we signed the contract with Exxon to do carbon sequestration. And that's been the biggest thing that we've seen on ways to decarbonize when it comes to manufacturing DRI. So when you're making steel, you do need some of the iron ores depending on the steel level quality and the requirements on the steel, especially when it comes to automotive and some of the grades that are required. But we looked at carbon sequestration. We also looked at hydrogen options for us as well. Currently, just with the price of hydrogen where it is and the amount of natural gas we would be using, having to switch to hydrogen, that wasn't a viable option for us. But we're really happy with the promising things through carbon sequestration that we're doing at that plant.
Thank you.
All right, who's next? Heath in the back.
Heath Crew with Forterra. For Magrathea, just had a question about your source of CO2 that you're sequestering with the mag oxide, and then also kind of what's the process by which you capture CO2? What's the source? How do you capture it? And then what do you do with the mag carbonate?
Could you go back? Mag carbonate? We're producing magnesium metal.
Right, but you
Oh.
were getting to negative
Oh,
CO2 by capturing CO2 with mag oxide.
okay, got it. Got the question. So we produce magnesium oxide, and there are actually several startups currently that are producing magnesium or trying to produce magnesium oxide solely to use for carbon sequestration by ocean alkalinity enhancement, and that is the route we're planning on going. Though that's not like the core technology we're building out currently, that is the path that we plan on use, basically through ocean alkalinity enhancement.
Producing magnesium for carbon sequestration, is that just a dial you can turn? Is what portion of the magnesium goes to product and which goes for carbon sequestration, or is it defined by the process?
Yes, exactly. So part of our dehydration process, and it's inherent to it, that some of that magnesium chloride will go to magnesium oxide instead of anhydrous magnesium chloride. And it just happens in the process that we have, but we are able to take advantage of that and use that to sequester carbon, and we can kind of control our yields, and we're working to understand that a little bit better to fully be able to dial that.
And there's another one, the 200 tons per annum, is that a commercially viable scale for that type of magnesium metal? I don't know anything about the industry.
So it's large enough quantities that we will be able to sell it. However, it's not commercially viable, and that will be an R&D facility to some extent. It's going to be located in the Bay Area. But our commercial plant will be about at least 10,000 tons per year, nameplate capacity. So it's significantly larger. And that's kind of the minimum size we're looking at.
And the reason I ask is that in the cement industry, there's people that are looking at electrochemical processes and taking basalts and other magnesium-rich minerals to get the calcium, and they're going to be producing hundreds of thousands, if not millions of tons of magnesium. And have you looked at their process and if it could piggyback onto that?
We have been looking at a lot of different byproducts of processes. I'm actually not sure. I don't think we've discussed with the cement, sustainable cement people, but would definitely be open to it.
Sublime and brimstone come to mind.
Yeah.
Right behind you, Steve.
Hi, I had a question about the steel making that Amari talked about. You talked about using a lot of scrap metal to make steel at Nucor, and also how that, together with other things, gave you a lower carbon footprint, and what would be the impact of people being as efficient as Nucor in terms of carbon. But is there enough scrap metal to go around? So that was the, or is it that you corner all the scrap in the world pretty much? And,
I think depending on who you're asking and whether it's a BOF producer or an EAF producer, that question may differ. But last year, the U.S. shipped over 13 million tons of scrap, exported over 13 million tons of scrap. So I think there's a lot of questions, and there have been a lot of studies around scrap scarcity if all of us transition from EAF producers to, or from blast producers to EAF. But at the current moment, especially in the United States, we don't see a scrap issue until minimum of 2050. We are still a large exporter of scrap. So currently in the US, about 70% of all steel making are EAF producers. The other 30% are more integrated producers. So the US as a whole has one of the cleanest steelmaking processes across the world, primarily because of how we produce EAF.
there must also be steel import into the US, right? Or so.
Steel, yes.
Yeah.
There are still imports into the US, again, depending on the market and what you're looking at. We would love for everyone to buy US steel. I think we could, between all the US steel making divisions, we can supply that. But yes, we do still combat steel imports and kind of, I would say, flooding the market with lower cost steel, depending on the country that's coming in. But the government has been really great with a lot of tariffs that's been in place to kind of stop that.
I think Matt or Hamed, did you have your hand up? Matt?
I had a question for Molly about your plastic. So it's biodegradable.
Yep.
And so a two-part question. So how long does it take to biodegrade? Under like what conditions? And then, so because it's biodegradable, does that limit it from being a food used in like food packaging, like plastic wrap or a bottle kind of stuff?
Yep.
I'm just curious.
Yeah, great questions. So PHAs will only biodegrade with significant enzymatic attack. So it can be used for all forms of food packaging and essentially most plastics, especially single-use plastics that we use. You would not want it in an application where there's a lot of microbial presence. So something like underground piping that could be exposed to soil. We do a lot of work in fashion. So if you have fibers and you're making it into apparel, if it's like a rugby jersey and you roll around in the mud and it's caked in mud and you put it in a plastic bag in your trunk and there's moisture in there, it'll probably start to biodegrade in a few weeks. Similar to cotton, actually, the biodegradation profile is similar to cellulose. So similarly to cellulose, if you have a leaf of a leaf, it'll biodegrade quickly. If you have a thin film of PHA, like a saran wrap type thickness, and you put it in an anaerobic digester, that'll last about 1 week, 7 days. But if you have a big log of wood and it ends up in the deep sea Arctic, it could last a very long period of time. Similarly, if you have a thick injection molded piece of plastic, it ends up in the deep sea Arctic, it could be years. I will note that the pathway to make PHA in organisms is more ancient than the pathway to make cellulose. So PHA is older than cellulose.
I think there was a question in the back corner over here. Yes, sir.
Michael Long Thermochemical. Question for Molly. You already got the mic. How stable, I know you're pilot right now, how stable are you feeling is your process for actual downscaling to the numerous methane emission slippage sources throughout the US? Is that a potential application? Do you feel like your bugs might be comfortable enough being downscaled to fit many of these small producers? Or are you more focusing on wastewater treatment plant, landfill, large methane emission locations?
Yeah, so to make a plant profitable, you probably need at least enough methane to make 5 to 10 million pounds of PHA. And if it really depends on the offtake of that PHA of where it's going and how much you can get. So that's more than like a single family farm would make, for instance. But if you have an agricultural facility that's maybe co-located with a creamery and you could digest the creamery waste with some manure, that could be enough methane supply to make a couple million pounds, so that could work. So one of the questions we're looking at is what is the smallest possible profitable plant? And it's probably something on that order of magnitude. And the bacteria can support that. That's not the challenge. The challenge is the overall economics of that unit and just the cash flow you're gonna get from that volume of material. But if you're like a creamery and you need yogurt packaging, and PHA would be completely stable in an application like that, you could imagine a world where you could make yogurt packaging and then that packaging could be co-digested with your creamery and manure, and you could close the loop on carbon if you were like a dairy company. That would be like the long-term future dream. But right now we're, using anaerobic digestion from a municipality to make designer sunglasses.
David, I see your hand up. Somebody back here? Nope, another one up here.
This is a question for Mango Materials. I was wondering, so what is your business model? You're going to license the technology?
Yeah, so right now we essentially purchase methane and we sell PHA. That's our current model. However, figuring out that lowest cost plant that I mentioned, and a lot of our customers would eventually like their dedicated plant. So like Nucor, they're located in São Paulo, Brazil. They're a large Brazilian cosmetic company. They would like a dedicated plant there. And they actually have a site of methane that could be used. And then they could have their own dedicated supply of PHA produced right there in Brazil. So in that situation, it would be a licensing model where Mango is providing the blueprints, the bacteria, the mineral media composition, which is really critical to get high levels of PHA. We have almost 300 standard operating procedures. We would be essentially like tech support, and somebody else would own and operate that facility, because at the end of the day, that's what's super challenging for companies such as mine, is we're competing with petroleum-based plastics. That is huge volumes, huge capital infrastructure and produces a really low cost material. And so rather than us needing billions of dollars worth of assets, that's one route to finance this with it not needing to be on our balance sheet.
Okay, I think that's going to be our time. We are due for a 20-minute break, and we're going to be back. Oh, she's saying 5 minutes. Does anybody have any more questions to ask? I'm told 5 minutes. Go on over here.
Hi, Richard Hart from ACEEE. Steve, you mentioned a couple of, well, there's a Senate bill and AB 2109, I think it was, that are sort of promoting best practices for the cement industry. And I was just wondering if the rest of you on the panel had any policy suggestions that you would like to see implemented that would be beneficial for the work that you're doing.
Sorry, that was to me?
Well, you mentioned, it was to all of you actually, because you're
asking if there are additional legislative measures that we'd like to see? Yeah, we're as the California cement industry, we don't have additional measures that we're ready to put forward right now, but we will. As we looked at on that slide from our roadmap to carbon neutrality, there are lots of areas where we're going to need help, right? The next couple of things that come to mind are alternative fuels, the ability to be able to use biogenic fuels, industrial wastes, and things like that in our facilities. Getting away from the traditional fossil fuels is going to go a long way, but there are regulatory barriers to being able to use those that we will need to remove. Anybody else?
I'm happy to comment and talk afterwards. I have a lot of thoughts on ways that legislation or regulation can make our lives a lot easier and level the playing field, which is just so complicated. I'd also mention that just biomaterials, biopolymers, there's lots of different types. I talked about PHA, that's one. There's PLA, that's another. It gets confusing really quickly. There's a lot of legislation out there that I think was really well intended, but that's creating actually a whole quagmire for startup companies like ours. I'd mention SB 54 right now is one of them. And it's like, honestly, kind of a hot mess. I guess it's a public comment, but it's like how we incentivize compostable materials and also the composters, which is maybe a little off topic for this conversation, but how they can make money, how everyone through the value chain can make money here, and also benefit like the new incumbent innovative materials that are up and coming. It's just, it's really challenging. And designing for end of life is something that like many PhDs probably have been earned and will be earned on this, but then translating that into meaningful action, and I'd even say LCA, which we talked about a lot in earlier panels, it's super complicated. And at the end of the day, our customer just wants to be able to put a number, like a very big negative number is what they want to say. And there's lots of ways you can do that, make the number look good. And you know, our customers are like, Mango, you guys are too nerdy and academic. Like your competitors out here giving us a much better negative number. And we're like, well, it's because of this, this, and this. And there's no like rules surrounding this. And I know there's groups in Washington trying to fix that, but it's not in our, like, trying to solve the plastics problem, not regulation.
I would say for us, we've supported a lot of the Buy Clean policies. So steel is really big in a lot of the Buy Clean policies that are happening, especially in California's Buy Clean policy. I think it was touched on in the last panel. There's so many different threshold values across, depending what state you're at. There's so many different GWP values that you have, depending on the emission factors that you're using, depending on how your EPD is done. It can change. So I think as we move into this space of Buy Clean and setting low carbon materials, just understanding how to standardize that across, also compared to, you know, when we look at Europe and their standards, a lot of things that happened in CBAM in Europe and how that's translating to what we're doing. But I think standardization would be very helpful as we understand everything on a level playing field, understanding truly what's considered clean steel, clean, low carbon products.
I think we have time for one more, as long as it's not too long a question. We got one, all right.
Another quick question for Nucor, correct? Sorry, I'm unfamiliar. You mentioned biochar. Just a big picture. How much biochar can the steel industry in the US actually handle before it's saturated?
I don't think I want to speak on the entire steel industry. So
okay, how about you guys?
And the big thing about biochar, the way that it feeds and the way it works, depending on how it's made. Right now, it's not a 100% replacement for virgin charged carbon, just because when you're feeding it into, I don't want to get too technical, but into the furnace and how well the carbon is absorbing and being able to get a good bath. So it just depends. We've been doing trials at different percentage levels to understand, okay, how do we have to change our efficiency processes to get to 100% biochar? So right now, just because it is manufactured different than your virgin carbon, there is a step process for us to even get there. So I don't think it would be saturated at the moment, just because there is a process to get mills to move to 100% biochar.
I'm just curious what the market is for this amount of biochars, or for your intake of biochar. You can assume 50% uptake or mixed with virgin, just to get an idea of the range. How many?
Yeah, so
millions
I
of
would
tons
say a
per
good
year with this
60-40 mix of virgin carbon and biochar currently, but depending on efficiency processes of your mill and what your, again, sheet, plate, bar, what steel you're making, that could look a little different. I'll totally talk to you offline about it.
All right, thank you very much, everybody, for coming. We're on to a 15-minute break, and we're back in this room at 3:40 for the closing plenary panel regarding the path forward. How about a hand for the panel here?